Okay, so we have collected some facts here. We collected the eigenvector equation, uh, PV equals lambda V, okay? And now we've collected this fact about matrices, that a square matrix A, if the determinant of A is non-zero, sorry, is equal to zero, if and only if AX equal to zero has non-zero solutions, okay? These two ingredients together are gonna allow us to, with a little bit of manipulation, compute eigenvectors. All right, so let's start with the eigenvector equation. PV equals lambda V. And don't get confused about the cast of characters here. P is a square matrix, it's n by n. V is a column vector, n by 1. And lambda is a number, okay? It's a constant. All right, so let's say that we have this, this equation here. Here's the move I'm going to make. Ready? I'm going to stick an identity matrix in between lambda and V. I'm allowed because you know that the identity matrix doesn't change anything, right? V, in other words, I can think of as being I times V. So I can equivalently write this as PV. I'm going to leave that side alone. Lambda times the identity times V. I is the n by n identity matrix, right? Remember, 1's down the diagonal, 0's on the off diagonal, all right? Next, I'm going to subtract lambda IV from both sides of this equation. And what do I get on the other side? I get the 0 vector, of course. Okay? And then finally, I'm going to factor out the V. You see the V, it appears in both of these terms on the right-hand side. So I'm going to factor it out in the right direction. All right? So I get P minus lambda I times V equals 0. Right? Nothing up my sleeve. This is correct. Okay? So now let's think. This here is an n by n matrix. P minus lambda times the identity is an n by n matrix. V is an n by 1 vector. And what we're saying is, to be an eigenvector, and remember, crucially, an eigenvector by definition is a non-zero vector V, which satisfies this equation. So in order to be an eigenvector of P, in order to satisfy this equation, what I'm looking for are non-zero solutions in V to this equation. Non-zero. Now this should ping the idea that we talked about here. If you have a square matrix and you want to solve AX equals 0, and look, we have a square matrix. I didn't call it A, it's called P minus lambda I. Square matrix. And we want to solve not AX equal to 0, but P minus lambda I times V equals 0. And we want to find non-zero solutions. So what we need to do is check when the determinant of A is 0. The determinant, in other words, of this matrix. Okay? So what we're going to concern ourselves with this matrix. Let me write some of these insights down. This equation will have non-zero solutions. If and only if the determinant of P minus lambda I is equal to 0. Another very important equation, this. Okay? The thing on the right-hand side, it turns out, is a degree n polynomial. And it's very important. This is a degree n polynomial. The determinant ends up being a degree n polynomial. And it's called the characteristic polynomial. of P. I don't know why I'm writing small like this, but I am. Okay? I'm saying this is a degree n polynomial. And it's called the characteristic polynomial of P. And what, okay, let's make sure that we understand. This is a polynomial in lambda. It's going to involve powers of lambda, okay? And you'll see that as a polynomial. It might not be obvious right now, but through computation, you'll see that. I'm kind of shoving this down your throat. It's a degree n polynomial. Now, what are we doing when we set that polynomial, this polynomial here, equal to 0, and then solving for lambda? We are finding the roots of that polynomial, the zeros of that polynomial, right? And if we can find a lambda which makes it, which has the property that the determinant of p minus lambda times the identity is 0, if we can find a lambda which makes that happen, then we can find non-zero solutions to this equation here in V, and therefore we can find non-zero solutions to this equation here in V, and therefore we found an eigenvector with eigenvalue, by the way, lambda. Tracing that backwards, if you followed that story, and you should rewind the video and watch it again if it doesn't make sense, what I'm saying here is that the roots of this characteristic polynomial are precisely the eigenvalues of P. I'm going to write that down because it's incredibly important. The roots of the determinant of P minus lambda times the identity are the eigenvalues of P. Okay? Isn't that cool? Well, you can't respond. It is cool. That's the correct answer. So this gives us the method. We are going to compute the characteristic polynomial, okay? And that's going to, and then compute the roots of the characteristic polynomial. And then using those roots become my eigenvalues. And then I can be on the hunt for the eigenvectors that we associate to those eigenvalues. Hopefully everything I just said right now makes sense. All right, so let's do one simple example. Let's start with a 2x2 example. Let's take P to be equal to 2, 1, 1, 2. Keep it real simple. Okay. Now, what I want to form is the characteristic polynomial. Characteristic polynomial. This is the determinant of P minus lambda times the identity. Of course, the identity here is the 2x2 identity matrix. So this is going to be the determinant of 2, 1, 1, 2 minus lambda times 1, 0, 0, 1. A little scary, but it's okay. We are not children. Well, maybe some of you are. And this ends up being the determinant. Now just do the arithmetic inside. What you end up getting is 2 minus lambda, 1, 1, and then 2 minus lambda. The determinant of that matrix. Are you with me? Oh, you can't respond. And then let's take the determinant of this. That's the product of the diagonal entries. So that's 2 minus lambda squared minus 1. You feel it? Honestly, what you're going to often do when you do these eigenvalue calculations is leap from here to here, okay? You're going to write, because it always has this form where you're going to be subtracting a lambda off of the entries in the diagonal of the matrix, okay? let's expand this out because we want to find the roots of this. So, and this ends up being a quadratic polynomial. What quadratic is it? So I think, I think we get, so if I expand this out, 4 minus 4 lambda plus lambda squared minus 1. And organizing this in a way that feels good to me, I like descending order, is lambda squared minus 4 lambda plus 3. And does that guy factor? So I need, yeah, oh yeah, look at that. I think it factors into lambda minus 3 times lambda minus 1. Okay? So the roots of the characteristic polynomial are 3 and 1. Right, well, so when I set, if I want, I can do this over here. So the roots of the characteristic polynomial are, when I set this thing equal to 1, so they're going to be given by lambda equal to 3 and lambda equal to 1. These are my eigenvalues. Of P. Okay? Now, what are the associated eigenvectors? This is the more computationally intensive part of what we're going to do now. You ready? Here we go. So I'm going to start with lambda equals, let's start with lambda equals 1. I think this is easier. So I'm just going to analyze this in turn. Now, don't forget, don't keep your eyes on the prize. What we are looking for is non-zero solutions to this equation right here. So we can form P minus lambda I, where lambda is equal to 1. So that's just P minus I in this case. We want to solve, in other words, P minus I times V is equal to 0. That's what we want to solve. Because solving that is what we're doing here, and that's equivalent to solving the eigenvector equation. All right? So we want to solve this. So let's write down P minus I. P minus I is the matrix. You can look here at this matrix. We know that's P minus lambda I, but now just make lambda equal to 1. So we get the matrix 1, 1, 1, 1 times V equal to 0. So the way that I'm going to do it is I'm going to make an augmented matrix. Like this. Now this is an exceptionally easy system to solve because we only need one row operation. I won't even label it. We're going to subtract from row 2, row 1. So we get 1, 1, 0, 0, 0, 0. In other words, we're going to add -1 row 1 to row 2. Okay? Now what is this saying to me? This is, if I think of V as having entries V1 and V2, then this is saying that V1 plus V2 is equal to 0. And as we discussed before, that second row, that row of zeros, is vacuous. It doesn't give us any information. Okay, so we just ignore it. The condition to be an eigenvector, in other words, is that V1 plus V2 be 0. There are tons of vectors which satisfy that, but I just want us to think about this systematically. What I can do with this equation is solve for either V1 or V2 in terms of the other. So for example, I could write V1 is equal to -V2. Absolutely true. And that's equivalent to what we have above. Okay? So then V, the solutions, have to be vectors of the form. Well, I can make V1 be itself, or maybe I think of it this way. I can make V1 be -V2 and then make V2 just be itself. And then I can find, V2 can be whatever it wants to be. So in particular, I can let V2 be 1. I could let V2 be 2. I could let it be 18,000 if I want to. And those would all be eigenvectors. But if in particular I let V2 be 1, then I get V equals the eigenvector -1, 1. That's my eigenvector that I'm going to take. All right. There are lots of choices. The only thing I can't choose is to let v2 be 0. Because if I let v2 be 0, then my resulting eigenvector, which is not really an eigenvector, is the 0 vector. And remember, by definition, I don't use that phrase lightly like some people, an eigenvector must be a non-zero vector, non-zero. Okay? Are you following? Now we're going to play the same game for lambda equal to 3. In this case, we solve p minus I. Well, we solve, in fact, p minus 3I, rather, times v equals 0. What's p minus 3I? Well, we just let lambda equal 3 in this matrix right here, right? And if we let lambda equal 3, we get the, and we make an augmented matrix, we get, I think, negative 1, 1, 1, negative 1, and then 0, 0 here. Yeah? It's still the case, because of course it is, that the second row is a constant multiple of the first. This will always be the case if you've done the characteristic polynomial correctly. It won't be the case in in bigger systems, like a 3x3 or a 4x4 system. It won't necessarily be the case. But in this relatively simple case, we do have this nice property that we'll always have, if we've done the characteristic polynomial correctly, that the two rows are constant multiples of one another. So one elementary row operation kills it right away. Negative 1, 1, 0, 0, 0, 0. And what we learn from this is that negative v1 plus v2 is 0. In other words, an eigenvector, v1, v2, has to satisfy this equation right here, this one, this one. So if I was to write down the eigenvector, it would be something like v equals, now, so I could write v1 in terms of v2. So this would be v2, v2. v1 is equal to v2 after all. And now I choose any non-zero value for v2. Let's choose 1, because why not? I don't have to. Wait, I don't have to. Why don't I choose v2 equal 2? I don't want to make it too complicated. Let choose v2 to v2. Then an eigenvector v is 2, 2. Okay? All right. So in other words, an eigenvector with eigenvalue 1, we computed, it's negative 1, 1. Is that the only one? No. We could have done negative 2, 2. We could have done negative 18,000, 18,000. That would also work. An eigenvector with eigenvalue 3 is 2, 2. Did it have to be 2, 2? No. It could have been 2,000, 2,000, for example. Okay? It could have been negative pi, negative pi. That would have also worked. Okay? As long as the two entries are equal to each other for this particular matrix, and this is very particular to this particular matrix, we get eigenvectors. As long as it's not 0, of course. Okay? All right. I think in the next one, I'll do a more complicated example of a 3x3 matrix. Okay? All right. See you in the next one.